For years, there was this one technology we all just trusted to keep our data safe. It was a cornerstone of storage. But what if I told you that today, that very same technology has become one of the biggest threats to everything you've saved?
So, that's the big question we're diving into. How on earth did the hero of data redundancy become the villain? Well, the answer isn't in some single dramatic flaw. It's more like a perfect storm, created by the absolutely insane growth of our hard drives.
All right, first up, let's get into why we all fell in love with RAID-5 in the first place. It was simple, it felt really smart, and for a very long time, it was the most efficient way to balance having lots of storage space with, being protected if a drive died. And here's where that efficiency really shines. With something like RAID-1 or mirroring, you lose half, literally half of your raw capacity just for that safety net. But RAID-5? Oh, it was a total game changer. You could have this big array of drives and only give up the space of one of them for protection. It really seemed like the perfect deal.
But lurking right under that shiny surface of efficiency, 3 fundamental flaws were just waiting. And as our hard drives exploded in size from megabytes to terabytes, these little flaws went from being a theoretical risk to, yep, that's definitely going to happen statistical certainty. So let's meet the 3 silent killers of RAID-5.
So killer number 1 is a deep architectural problem called the write hole. Just imagine this. Your server loses power right in the middle of saving a file. It manages to write the new data, but not the new parity. And that parity is the special math that lets you rebuild the array if a drive fails. When that write gets cut off, the whole system reboots into a state of just total confusion.
And here's the real danger. Your RAID controller looks at the data at its parity, sees they don't match, but it has absolutely no way to know which one is the right one, the most recent version. So that one piece of your data protection, it's now completely useless.
Now, this second killer, this is where things get genuinely scary. It's a statistical time bomb. It's called an unrecoverable read error, or a URE. And here's the thing. Every single hard drive is rated to have one. It's not a question of if it will happen, it's a question of when.
Okay, so a 1 in 100 trillion bit error rate. That sounds incredibly reliable, doesn't it? It seems so small you could just ignore it. And for one tiny file, sure. But what happens when you need to read a lot of data all at once?
So when you do the math, that tiny error rate means you are statistically likely to hit an unrecoverable read error after reading just 12.5 terabytes of data. Burn that number into your brain, 12.5 terabytes.
Okay, here's the punchline. When a single 8 terabyte drive fails in a pretty typical RAID-5 array, the controller has to read all the data from the remaining drives to rebuild it. In this very common example, that's 24 terabytes of reading. That is almost double the amount of data we just said it takes to statistically guarantee a failure. And this right here is the heart of the problem. Your array is built to survive one drive failure, but during the rebuild, the most stressful, most vulnerable time for your data, it's statistically guaranteed to hit a second fatal error. That isn't bad luck, it's just bad math. The system is basically designed to fail. All right, our third killer is the sneakiest of them all, bit rot. This is when the data on a drive just quietly degrades over time, but the drive itself has no idea anything's wrong. It'll hand you corrupt data with a smile, telling you everything is A-OK.
And here is the absolute kicker. The one tool you have that's supposed to help, a consistency check, can actually become the weapon that destroys your data. The RAID controller sees the good parity doesn't match the rotted data, assumes the data must be right, and so it fixes the parity. It has just permanently baked the corruption into your array, and in the process destroyed your only hope of ever getting the original file back.
So, yeah, RAID-5 is fundamentally broken. What's the fix? Well, the answer isn't just a slightly better version of RAID, it's a completely different way of thinking about data, and it's called ZFS.
This quote from the source material is so important. People often ask how RAID-Z1, the ZFS version of RAID-5, compares, but that's missing the forest for the trees. RAID-Z is just one feature. The real magic, the actual solution to all these problems we've talked about, is the ZFS file system itself.
So how does this new philosophy actually take out those 3 silent killers?
Well, it doesn't just put a Band-Aid on them. It tackles each one at a deep, fundamental architectural level.
Remember the write hole?
That was caused by writing new data on top of old data. ZFS has this simple, brilliant solution. It never overwrites data. Ever. This is called copy on write. When you change a file, ZFS writes the new version to a brand new, totally empty space on the disk.
And this whole process is atomic, which is a fancy way of saying it either finishes completely or it doesn't happen at all. So if the power cuts out mid-write, no problem. The master pointer to your data never gets updated, so when you reboot, the system still points to the old, perfectly valid data. The write hole isn't patched, it is architecturally impossible.
Now, what about that silent corruption? Well, ZFS gives every single block of data a checksum. Think of it like a unique digital fingerprint. But here's the genius part. It stores that fingerprint with the data's parent pointer. This creates something called a Merkle tree, which is basically an unbreakable chain of trust. When you read a file, ZFS checks the data against its trusted fingerprint. If they don't match, it knows, without a doubt, that the data is corrupt, and it can use its redundancy to fix it right then and there. Okay, so ZFS has solved the write hole and bit rot. But what about that ticking time bomb, the URE that happens during a rebuild? This is where ZFS makes a huge shift from reactive repair to proactive integrity.
See, a RAID-5 consistency check is so dangerous because it blindly trusts the data. A ZFS scrub does the exact opposite. It trusts the math, those cryptographically secure checksums. So on a regular schedule, a scrub just reads through all your data and validates it. If it finds a hidden error, the very same URE that would kill a RAID-5 rebuild, it finds it early while the array is still perfectly healthy and just automatically fixes it. It's diffusing the time bomb months before it ever has a chance to go off.
Which brings us to the final verdict. We've seen how ZFS as a system is just vastly superior. But is RAID-Z1, its direct single parity cousin to RAID-5, is that the complete answer we're looking for? Let's break it down. ZFS with RAID-Z1 completely solves the write hole and silent corruption. They are gone, by design. But when it comes to URE rebuild failures, it only mitigates the risk. Why? Because at the end of the day, it's still a single parity system. If a brand new error pops up during that rebuild after your last scrub, well, you're still in a whole lot of trouble.
And this is really the final thought I want to leave you with. With the gigantic drives we have today, just protecting against a single drive failure isn't good enough anymore. The real question you have to ask is, can your data survive the recovery process itself? For modern data safety, the true solution isn't just ZFS, it's ZFS with dual parity, which you'll know as RAID-Z2.